everyone, to the Algebraic Graph Theory Seminar. This week we have Judi McDonald talking about skew-symmetric characteristic polynomials of cacti.
So thank you, everyone. It's wonderful to be a part of this seminar, both as a audience member and now today I wanted to share with you PhD work that a former student of mine did, and Matt Hudelson was co-supervisor with me, and he's here today. So I'd like to take a few seconds to introduce Matt, and Matt, jump in anytime I say something dumb, which may be a lot of interruptions, but we'll see how it goes. When Paula gave her talk, one of the questions people asked at the end was, well, why'd you pick cacti as sort of the thing you want to work on next? So I'll try and explain a little bit of why cacti seemed like an obvious choice from this other thesis. And I'm going to start with presenting, assuming I have a lot of graduate students who may or may not have seen the Harry-Sachs formula. I want to go through my favorite tool when I'm working with characteristic polynomials and graphs. And I'm a digraph person, so I have to think digraph, and then I can translate it into graph theory. So, and I'll try to put di in front of anything that's a digraph type object, and no di in front of anything when I'm referring to a graph that is just a single edge between vertices, and more typical, I think, of the types of talks I've seen so far. So here's the idea. I take my favorite matrix A, n by n matrix, because we're going to talk about characteristic polynomials. And whenever I have a non-zero entry, like here the 1, 2 entry is non-zero, I'm going to draw an edge from 1 to 2, and I'm going to put whatever entries in the non-zero entries in the matrix, that's going to be the weight of my edge. So I pretty quickly get a weighted digraph, which I'm guessing most of you are familiar with. And now I can go ahead and try and link this to the characteristic polynomial. And I'm going to label my characteristic polynomial so that the coefficient of x to the n minus 1 is a1, coefficient of x to the n minus 2 is a2, and aj is going to be the coefficient of x to the n minus j. So if I go ahead and take my characteristic polynomial here of the matrix at the top, let's look and see if we can see some patterns to relate the graph to the characteristic polynomial. So let me close up this middle part so it's not quite in the way. So -6 was the entry coefficient of x to the n minus 1. And if we look, I've got 3 loops, so 3 1 cycles, weighted 2, 1, and 3. If I add those up and negate it, I get -6. 5 was the coefficient of x to the n minus 2. And I can create disjoint cycles of total length 2 by pairing my loops. So I've got a 2, 3 loop, the 2 loop, weighted with 2, weighted with 3 loop, the weighted with 2, weighted with 1 loop, and the weighted with 1, weighted with 3 loops. So I got 3 pairs of loops, and then I've got an actual 2 cycle sitting here. So weighted with a 2 and a 3. So it turns out my 5 can be put together using these disjoint cycles total length 2. And we'll talk in a bit about the sign, but let's go through one more. So to get my coefficient of x to the n minus 3, I can put my 3 loops together. I can put a loop with a 2 cycle. So I've got that a couple different ways, as long as they're disjoint. And then I can use actual 3 cycles. So here we go. We got 3 cycles in this graph, I think. And as long as I get the signs right, I can put this together and it gives me my coefficients of n minus 3. So getting up to n minus 4, I'm going to go through a couple just because it's relevant. So now I've got a bunch of 3 cycles, for example, and I can pair them with a loop to get total length 4, but it has to be disjoint. So for example, if I take the 2 cycle here on the right, I cannot pair it with the loop on 4 or the loop on 5. I can only pair it with the loop on 1 so that it's disjoint. So that's the idea. And it turns out that I can get the jth coefficient by collecting all disjoint cycles total length j into sets Sj, and then I pull one out, and for each, and I'm going to add up for each different set of disjoint cycles. I'm going to add those up, and I'm going to pull out my collection. And for each cycle, now I'm going to take the weight of this. I'm going to weight the cycle, which is just the product of the weights on the edges, and then I'm going to negate it. So if I have just one cycle in my group, I'm going to get a negative. If I have two cycles, it'll turn out to be a positive weight. If I have three cycles, it'll turn out to be a negative weight. And that gives us the right pattern up here of positives and negatives in my cycle, in my coefficient. So I'm collecting, so for example, when I did the n-4, I'm collecting all the different ways I can put together a disjoint cycles of lengths 4. So for example, I have loop, loop 2 cycle, I have loop 3 cycle, and that's kind of the general types of patterns that we get to make up 4. And then I sign them based on the fact that here I had 3 disjoint cycles, so it's a negative. When I did a loop times a 3 cycle, there's only 2 disjoint cycles, so it gets a positive weight on the front, and so on. So we can tweak this a little bit. If we're looking more at the adjacency matrix of a graph, things get a lot easier, because on one hand, all my weights are 1. And I'm a digraph person, so when I see this matrix, I still see a digraph with edges going in each direction and a weight of 1 on each edge. So if we look at this particular characteristic polynomial, we know the 2 cycles are now edges, and I can only go around an edge 1 direction. So it shows up just once, so a weight of 1. If I look at the 3 cycle, it's actually going to contribute a weight going around clockwise, and then we get a contribution going around counterclockwise. So every time we run into what adjacency matrix people call a cycle, so for me, directed cycles of length 3 or greater, it's going to contribute twice, once in the clockwise direction, once in the counterclockwise direction. The edges are just 2 cycles, so they're going to contribute only once, because I can't go, there's only one way to go around the 2 cycle. There's not a forward direction and a backwards direction. So we can update our Harari-Sachs a little bit to just be, now as I'm looking at my cycles in my disjoint class D, I need the number of elements, so the number of disjoint cycles, including, and I said elements here because I got to count the edges and the cycles. The edges are going to just multiply our weights by 1, so we don't even have to worry about them. And then our genuine 3 or bigger cycles are going to contribute twice, once in each direction. So our formula gets simplified a little bit, and different times when I've tried to, tie down the history of Harari-Sachs, this is a popular version of it that I see frequently in the literature, more frequently than the more general version that I presented above. So one of my graduate students, Liz Bodine, went to a graduate summer workshop put on by Leslie Hogben, and came back with this idea of, well, instead of weighting our matrix, I probably could go through that, but sorry, I got ahead of myself. So if we look at this particular graph now, my counting's a lot easier. There's no loops. So coefficient of x to the n-1 is 0. The -7, I count up, I've got 1, 2, 3, 4, 5, 6, 7 edges. So the coefficient of x to the n-2 is just the negative of the number of edges. When I look at my 3 cycles, again, I've got 3 cycles. Remember, I have to double it because I can go in either direction. So I get a -6 and so on. So getting our characteristic polynomial using an adjacency matrix goes a fair amount quicker than when we were working with a general weighted digraph. Okay, so now on to the story of how I got into skew symmetric matrices. So Liz went off to this workshop run by Leslie Hogben, and came back talking about skew adjacency matrices. And the idea with a skew adjacency matrix is instead of weighting the edges 1 and 1, I'm going to weight the edges 1 and -1. So every time I've got an edge in my regular graph, in my digraph, I've got 2 edges, 1 in each direction, and the game is to always pick one to be 1 and the other one to be -1. So I've got the absolute value of ajk is 1 always, and then the product of ajk with akj is -1. And then whenever there's an edge and whenever there's not an edge, we're just going to throw a 0 into our matrix. So let's go a little slower because this is sort of the theme of my talk. And let's see how this affects the structure. So if I've got an edge, it's got weight -1, right? Because one direction is always going to be -1 and the other direction is always going to be 1. And then remember, when we're putting things together in a Harry-Sachs formula, we negate the weight. So edges are always going to contribute a +1 to our formula. So edges behave very nicely in these skew adjacency matrices because you don't even have to keep track of the sign because it's always positive. And when I went to a Beers workshop where we worked on ways to tell cospectral graphs apart. And so I said, hey, let's try this idea of throwing in 1s and -1s. And it worked out really well. I went off with the first, small cospectral graphs, and everything was going swimmingly until we got to the point where we had two graphs, cospectral graphs with only odd cycles. And here's what goes wrong with odd cycles. If I go around in the clockwise direction, so in this particular, I got a 3 cycle here, I'll get 1, 1, -1. So its weight is -1. And its weight is -1 because I've got an odd number of -1s going in the clockwise direction. Well, if I've got an odd number of -1s in the clockwise direction and an odd number of edges, that means I've got an even number of -1s going in the counterclockwise direction. So I get a 1, a -1, and a -1. And when I multiply those together, I get a +1. So in the clockwise direction, I get a negative weighted product. In the counterclockwise direction, I get a positive weighted product. And when you think about what happens to Harari-Sachs, every time this cycle has 2 dicycles, one positive, one negative. So every time this cycle shows up in Harari-Sachs, it's going to cancel itself out. Because remember, the forward dicycle is going to get added with whatever else it's going with, is going to get added to the backwards dicycle with exactly the same things added. So it turns out that odd link cycles in this skew environment contribute nothing to the characteristic polynomial in the end. By the time you've added everything up, they've just canceled out and they're gone. So not very helpful because they just disappear. So let's look at what happens with even cycles. So even cycles do a little better. So if I look at my cycle on the left here and I go around the forward direction, I've got a 1, a -1, a -1, and a -1. So I've got 3 -1s. I've got a negative weight overall. If I go counterclockwise, I'm going to have a 1, a 1, a 1, and a -1. So still a negative weight. So whatever terms this 4 cycle shows up in the characteristic polynomial, it's going to show up twice with a weight of -1 each time. So it's going to contribute a -2. And then I got to negate that. So it contributes a +2. So in general, this +4 comes out of 2 edge pairings. I can pair the edge 1, 4 with the edge 2, 3, and I can pair the edge 1, 2 with the edge 3, 4. So I get 1 + 1 is 2, and then I get this negative of -2, giving me a +4. So whatever happens in the clockwise direction, exact same weight, total product weight is going to happen in the negative direction. So this one, we had negative weights total. If I switch just one edge in this cycle, I'll get a -1, -1, -1, -1. That's all multiplied together gives me a positive 1. And in the reverse direction, I'm going to get a positive 1. So very quickly, we see that this is going to contribute a weight of 2. And remember, I have to negate the weight. So a weight of -2. So my 2 edge pairs added to +2. Now my 4 cycle gives me a -2. And so that term, the constant term, disappears out of the characteristic polynomial. So for an even cycle, just a plain old everyday even cycle as my graph, I'm going to get 2 characteristic polynomials. One, when I've aligned the ones in -1, so when I go around the cycle, I get a positive weight, and one, so when I go around the cycle, I get a negative weight. So just to summarize, the contribution to the characteristic polynomial from edges and odd cycles does not change, even when we flip ones and -1s in the directed arcs. But when we change ones and -1s that affect the weights on the even cycles, that's going to lead to changes in the characteristic polynomial. So an interesting question, an obvious question, is how many different spectra or equivalently characteristic polynomials? You know, when we started this, we were calculating the eigenvalues over and over, and then we went, why are we working so hard? Why don't we just stop with the characteristic polynomials and be done? So, and then Harry-Sachs became a really valuable tool in sorting things out. So our question is, how many different spectra or equivalently characteristic polynomials can be realized by a skew symmetric matrix associated with a given digraph? And we're just going to refer to the number of characteristic polynomials associated with a given digraph as its skew number. So I'm going to go ahead and talk about the skew number of some different graphs. So always start small, always start easy. Tree always has a skew number of 1. If I've got a cycle, it's either odd or got an odd number of edges or an even number of edges. If it's got an odd number of edges, we're going to get a skew number of 1. If it's got an even number of edges, we're going to get a skew number of 2, depending on whether we weight it so that the product is a positive 1 or a negative 1. So moving up a little level of sophistication, we decided to look at cactus, because we learned very quickly that if you try to do the whole problem at once, it's just overwhelming. So the idea of a cactus is you've got no 2 cycles sharing an edge. And this is nice because then when you flip an edge, you're only trying to keep track of what it does to 1 cycle. So here's a cactus. You can see we can link our cycles with at vertices, but we want to not let them overlap with an edge ever. This is not a cactus. And if you start to think about it, if I flip this middle edge, I flip the sign on 2 4 cycles. If I flip an outer edge, I'm flipping the sign on a 4 cycle and a 6 cycle. And so it gets very complicated to track what you're doing. And Amy thought it was very funny to include this picture of, it's an artistic rendition of cacti, so it's not a cactus. So that was her favorite injection of humor into her dissertation. So we amended our question quite a bit so that we could get a hold of it, because otherwise we just couldn't get a hold of it. It was too wild. There were too many things happening, too many things going different directions. And this proved to be an interesting, sometimes you simplify it too much and then it's like, oh, the answer is obvious. This is not a good dissertation topic. So we simplified it down to only looking at cacti. We're going to classify our cacti by the number of even cycles. So we're going to look at cacti with k even cycles. And we're even going to say, well, let's just make all the cycles have the same length, again, so that we can keep track of them. So our first lemma is if I let S be the skew number of cactus with k even cycles, each cycle's length m, then S is between k plus 1, so 1 more than the number of cycles, and 2 to the k. So let's just check quickly why. So first, if I look at the coefficient of a to the j, it's going to be 1 times however many sets of m over 2 disjoint edges I can put together, plus 2 times the number of negatively weighted n cycles minus 2 times the number of positively weighted M cycles. Since there are K plus 1 different possible distributions between negatively and positively oriented cycles. So for example, I can come in and have all my cycles positively oriented. Then I can come in and have one of my cycles negatively oriented and the rest positive. And then I can have 2 negative and the rest positive and so on. So K plus 1 different possibilities there. So that gives me K plus 1 different values for a to the j. So I know for sure my skew number's got to be at least K plus 1. Well, what's the most it can be? So if I've got K even cycles and there's 2 possible weights for each even cycle, and that's the only thing, changing the weights of one of those cycles is the only thing that will affect my characteristic polynomial, the maximum has to be 2 to the k. So we pretty quickly got bounds on what our skew number can be. And then the question is, well, can equality hold? Is this a strict inequality? What gives you sort of the power to hit each end? So Dutch windmills turned out to be very, very useful in this problem. So if you look at my Dutch windmill, it's got complete symmetry between all the cycles. So it doesn't matter if I make the first cycle negative and the other 4 positively oriented. That's going to be the same thing as if I made the second cycle negative and the other 4 positively oriented. So it's pretty clear or pretty easy to show that if you've got a Dutch windmill with, in this case, my blades are even length, then the skew number is going to be K plus 1, just because there's so much symmetry in how these cycles are contributing to the characteristic polynomial that really all that matters is how many do you have positively oriented, how many do you have negatively oriented. Your characteristic polynomial is completely determined by that relationship. So what about the other end? Well, we like Dutch windmills. They've been pretty handy. So if I go ahead and now if I want to destroy this ability to have symmetry between all of the cycles, what I can do is just come in and throw on, and I'm going to take a screenshot so I can draw on it. Okay, so here we go. Here's my screenshot. I can go ahead and just pop an edge on this cycle. So now what's going to happen is when I include this edge, so let's do, so my blades are length 4. So if I look at the coefficient of x to the n minus 6, I can put in this edge and pair it with the other four cycles to contribute to the 6th cycle. And then flipping this edge doesn't change that number. Flipping, the sign of this particular cycle will not change the number of the coefficient of x to the n minus 6. So using these, what we call decorations, I can now start to pair how my cycles behave in a different way. So if I put an edge on, add an edge to the end of 2 of these blades, then I see that I'll have 2 paired one way and 3 behaving the other way. So in general, if K1 to KL is a partition of K, so remember K is the number of even cycles I've got, and I put KJ, I take the KJ blades and I throw on J leaves. So here my partition is 2, 3, and I've thrown on 1 blade on the 0 blades on the K1 and 1 blade on the K2, and so I could go up to 1 and 2 equivalently. Then the skew number is going to turn out to be K plus 1, K1 plus 1, K2 plus 1, KL plus 1, and I multiply those all together. So here I've got a 2, 3 partition, and you're right, I should technically be putting 1 more edge on each of the blades to be the way I described it. So maybe we should say K blades each with J minus 1 leaves. Then I'm going to get a decorated Dutch windmill with skew number 12. So let me get out of my screenshot here. Okay, so I'm going to write j minus 1 here so it matches the picture I drew. So in the first one, you don't do anything, and then the second one, you put on one edge and so on. So composites seem to be pretty easy to get. And at first we were kind of like, well, that's, oh, sorry. If I do a 1, 1, 1 partition of my K blades, so nothing on the first blade, one edge on the second blade, two edges on the third blade, and so on, I get 2 to the K different characteristic polynomials. So our Dutch windmills and our decorated Dutch windmills give us the endpoints, my least number and my most number. And we were really naively hopeful that this was the whole story. You know, I can get all these composites in between just by altering the symmetry of the cycle, and that should be about all I can do, right? So does that tell me, once I've destroyed the symmetry of the cycles, I should have some sense of how they affect the characteristic polynomial. So our naive first conjecture was just, we can get the endpoints and we can get this composite numbers that are achieved by using a partition, and that's all you can get. So in any linear algebra problem, at least for me, if you don't know what's going on in the lower dimensions, you can't expect to have a good conjecture, right? If it doesn't work for small dimensions, it's not going to work in general. On the other hand, for small dimensions, you can kind of brute force things. So you can sort out what's actually going on in small dimensions just by pushing through your brute forcing it. Small enough you can get a hold of everything. So start small. If I've got one cycle, if it's an even cycle, I get 2 characteristic polynomials. Well, if K is 1, that's both my upper and lower bound. So doing great. My cacti, my Dutch windmills have turned out to be the cacti that work perfectly for K equals 1. And for K equals 2, same story. I've got a Dutch windmill with 2 blades gives me the lower bound. And if I throw an edge on one of those blades, I get what we were calling a fully decorated Dutch windmill. It gives me the other bound. Okay, well, moving right along, our Dutch windmills are doing a great job for us with a little bit of decoration. So if I move up to 3 even cycles, my lower bound is 3 plus 1 is 4, and my upper bound is 2 cubed or 8. So my Dutch windmill with 3 blades gets me the lower bound. I can decorate one of the blades, leaving 2 plain, that gets me 6, or I can decorate all 3 blades differently, giving me 2 to the 8. So what about 5 and 7? So I think we worked for a long time trying to prove that you couldn't get 5 as a skew number. And after a while, when you try to prove something for a long time and it doesn't work, you start looking at examples again and trying, right? I think a rule of thumb when you're working on a conjecture is, you know, you have to have a ratio of you work to prove it's true this many days, and then you work to prove it's false this many days of the week, or you're going to end up putting a lot of energy into proving that something works when in fact it's false. So at some point we decided trying to prove it was true wasn't going so well, so maybe we should look for examples. And my favorite example we came up with, we call a peacock. So a peacock has a head and some top-notch feathers and then a very nice tail. And it turns out this peacock has a skew number of 5. And in general, if you cleverly choose it doesn't work with any number of tail feathers. You have to, or pardon me, any number of feathers in the head notch. You have to get the exact right number of feathers in the head notch. Then we get a skew number of 2k minus 1. So this was really nice. This was the first time we had a good way of creating graphs so that the characteristic polynomials were not composite, not always composite. Not that 2k minus 1 can't be composite, but at least now we were getting some primes. And then the tail down here is a Dutch windmill. So why not decorate it and see what happens? And so we can go ahead and decorate the tail of our Dutch windmill, which the peacock really likes, right? Because the peacock loves to have a very impressive tail. And so in general, peacocks with the right number of head feathers and a tail that is a decorated Dutch windmill, if we know the skew number of the Dutch windmill, let's say it's S, then the skew number of the peacock is 2S minus 1. So this turned out to be pretty effective for us. So if we go back to our table with 3 even cycles, the peacock fills in 5, and the peacock with a what I'll call a 1-1 tail partition fills in 7. So going swimming, so now, right, our original conjecture was pretty cynical. It was like, yeah, there's going to be a lot of holes. It's going to be really difficult to get anything but these the bottom, the top, and some composite numbers in between. So let's move up a size. So let's look at 4 cycles. So for 4 cycles, my lower bound is 4 plus 1 is 5. My upper bound is 2 to the k, which is 16. I've got my Dutch windmills, so I can go ahead and fill in 5, 8, 9, 12, and 16 with my Dutch windmills and my decorations of Dutch windmills. And you'll notice in my original drawings, I was sticking the edge on the end because we wanted to do this with any size of cycles on our Dutch windmills. We started just throwing the edge on one off from the center so that we didn't have as much trouble keeping track of where this edge was affecting things. Okay, so I've got my Dutch windmills. Then I've got my peacocks with Dutch windmill tails. So that fills in for me 7 and 11 and 15, depending on how I decorate that tail. So that leaves me with a few holes. And so we, I think we resorted to brute force, and one of Matt's other students who loved to write programs wrote a program for us that went through and checked for k equals 4 all the possible cacti without too much extra stuff stuck on with 4 cycles. And we identified a couple more families. So now we went ahead and we, today these look like dueling hummingbirds or something, but this was a pattern we found pretty useful. And I think we called them some kind of pinwheel, maybe. In any case, these turned out to be very useful, and we could decorate so again, we're kind of just sticking 2 Dutch windmills together by the center. And again, we could decorate the edges of this Dutch windmill a lot of different ways. And then the other group we found, we called them Cacti Pillars. So just stringing a bunch of cycles together to look like a cacti and maybe putting some feelers on the front. So these also turned out to be really useful and predictable patterns. And we discovered, in addition to our, sort of mainstream cacti with strung together cycles and edges, we could also throw decorations in clever places and shift the characteristic polynomial and how it's behaving. And so the Dutch windmills were really easy to understand how it's affecting the characteristic polynomial. These cacti and double Dutch windmills and Cacti Pillars were much harder. It wasn't as obvious why sticking an edge here gives us enough variation in where these 4 cycles contribute to terms in the characteristic polynomial to give us 14 different skew symmetric polynomials, as opposed to the more obvious 5, 8, 12, and 16. And same with the peacock. Why, when you get the head feathers just right, does the tail suddenly start to contribute in different ways than it did in the Dutch windmill? So why can I take this and go from 5 to 7? just by cleverly putting head feathers on this particular peacock. And so the intuition became a lot harder. Like what is it about, how do we go about finding something like 10 or 6? And the K+2s, I think, turned out to be some of our biggest challenges. Like they seem to be harder to get, because as soon as you start adding some lack of symmetry, taking away symmetry in your cycles, it jumps up by too much. They affect too many different places and you can't get a low number. So this turned out to be pretty good work, and Matt and I felt like enough work for a dissertation. So we ended with the conjecture that every skew number between k+1 and 2k can be realized by a cactus, and you can keep it simple. We can have k and we can have them all be 4 cycles. It really didn't make much difference if we were dealing with 4 cycles, 6 cycles, 8 cycles, 10 cycles. The size of the cycle in a cactus really didn't change the problem. So that's the conjecture that we ended with at the point in time that Amy successfully defended her PhD. And we kind of have been waiting around a bit to see if she'll pick up with her thesis problem and want to do something with it. And I think it's getting long enough that maybe we'll start to look at this again and see if we can write it up for publication, because it's a neat problem. It's a curiosity driven problem, but I think a pretty interesting problem. And a little bit short on time, but that's kind of sums up what I had to say on the problem, and I'd love some questions.
Thank you very much. Are there questions for Judi?
The only thing I'll add is I remember 13 was the hardest number in that list, and that was the one that Ben, my student, found. That lovely
half-starved caterpillar.
Yeah. that was the tough one. I think the other numbers we were able to get without too much computer assistance, but that number 13, I remember Judi, you thought that was a hole that was not ever going to be patched, and then Ben found it.
I did. I was really cynical on this problem for a long time. I really thought, no. There's got to be a lot of holes. And now I've gone the other way. Now I think if you're clever enough or lucky enough.
Well, what makes me wonder is there, much like the 2s-1 type situation, is there some kind of clever way of putting an attachment on that will simply double the number, and that way you get an interweave? You just take the previous case and then just interweave the 2 answers. So that would be, at least looking at it one more time, a direction that we can think about.
That would get us a lot more, but remember, we can't get every S. When we do that 2s-1, the S's come out of the decorated Dutch windmills with 1 fewer cycle.
Right.
So we don't have solid, the S is not solid either. So ironically. Yeah, it's not all discrete possibilities. So anyhow, we had a lot of fun with this. Harry-Sachs, as I mentioned at the beginning, is my favorite tool for working with characteristic polynomials, and in particular predicting how those characteristic polynomials behave. And I know we've seen lots of talks of people working on quantum, and the frustrating part with quantum is knowing the characteristic polynomial isn't enough, right? We have to know more about in particular, the eigenspaces and how they're lining up, how those eigenspaces are behaving relative to each other. So it's not quite as powerful in the quantum mixing and state transfer kind of problems, but I still wanted to share with this group, because I know everybody likes to play with graphs and play with algebraic properties of graphs. So yeah. Do we have any more questions? Anybody want to ask anything about Harry-Sachs or?
Hi, Judi. I've got a possibly naive question.
Sure.
Thanks for the talk, by the way. You mentioned computer searches, but if you're looking at graphs with exactly, I don't know, K4 cycles or whatever numbers you want there, there's no upper bound of the number of vertices. Is there some kind of construction you can do to show that like making really long induced paths doesn't matter?
I'm going to pass that to Matt because it was his student that helped us with this.
Yeah, I don't remember the parameters that Ben put into his search. I think just simply adding edges along the caterpillar isn't going to do much to the numbers that we're looking at here. It's more, I mean, except for the decoration edges. But honestly, this is so long ago, I don't remember the exact parameters that he used. So I don't have a good answer of how we limited the number to be less than infinity.
Yeah, I noticed in one of your examples, you have an edge, like if you take a leaf and add it to one of your leaves, you never have that kind of structure in your examples.
Yeah, there's no reason to tack on a P2 or a P3 to expect anything different.
Okay.
So yeah, you're basically limited to tacking on single edges to your base body.
And Paula's not with us today, but I think Paula has Ben's code. So Paula might know how, what kind of parameters Ben was using, because Paula's working on the mixing matrices of cacti. And so she was like, you know, it'd be really handy with the lower dimension ones to be able to look for patterns and lower number of cycle type cacti to look for patterns. And so Paula may be able to answer that if we ask her next week, but I think she's traveling right now. So
okay, thanks.